and she will introduce our guest speaker, and we're really looking forward to a wonderful talk. Young-Kyung Cho, sorry, I didn't add your last name too. Thank you. So Young-Kyung, take it away.
Thank you, Beth, and thank you for coordinating all this. Today I'm happy to host and introduce Dr. Sungsu Ray Hong, and he goes by Ray, and as you can imagine, he is Korean. He is an assistant professor at George Mason University. He works at the Department of Information Sciences and Technology, and his general area of research is HCI and CSCW, specifically focusing on bridging the gap between humans' mental models and the way that AI operates. So before his assistant professor role, he did his postdoc at NYU, and before that he did his PhD at University of Washington's Human-Centered Design and Engineering, and that's when I got to meet and know Ray. So today he will be talking about this interesting topic, empowering humans to steer deep neural networks with human-in-the-loop approaches and interactive tools. So Ray, please take it away.
Sure, thank you, Eun-Kyung. I'm gonna share my screen. Well, so yeah, I really missed the moment when I was in University of Washington. I saw Eun-Kyung at the time when I was in first year, but she was a superstar already. So wow, it's very difficult to talk with her. Well, besides that, I really am happy to just talk about my research directions, and I hope that my talk can be useful for our future collaborations and then research in general. And sorry for the change, but I changed my subject towards alignable AIs, helping humans to better understand, steer, and use the deep neural networks. So let me just talk about me. This is some kind of the landscape that Sundai Pichar discussed in the 2016 Google I/O, that our life has been shifted by computer science innovation every 10 years or so. Well, I think that I was so fortunate that I just see all of this kind of shift in my life. 1980, we had PC. 1990, now we are connected using web. Now 2000, we had mobile. And then just now 2010, we had big data. And then now there's a lot of information. And then nowadays, more or less from the 2012 to 15, now AIs and then especially deep neural network has been commercialized and then just come to our life very closely. Well, and the reason that I really just felt I really want to do the human factors in HCI was because while I'm just growing and then just interacting with those technologies, I really found the successful technologies really just designed for humans, while the failed kind of the things that will be disappear is against the humans. Well, so like PC, I was so just I had some frustration whenever I see this blue screen, whenever I just see. And I think that nowadays we cannot see this blue screen like in 1990s when I was starting just using this web, that was a dial-up modem and then just bulletin board system with the terminal. It was not that easy for me, especially persons who never just used the computer. And I guess now the interactive tools and then screens just help, the GUI help us to really interact with all these things and then easily. Mobile device, I just started working Samsung research around like 2000, middle of the 2000, and this is one of my kind of the projects I was involved in. Well, to be honest, this was not very impressive. And then everything has been just really just changing ever after Steve Jobs introduced his kind of mobile phone and iPhone. And actually that was really just beneficial to human beings in general. So I think that these are all kind of things happening. And 2010, we are having the era of the big data. Well, so that the information overload is going on, very, very difficult to understand what's going on. But I guess the researchers of human factors, we have a real just great opportunity to benefit people using the interactive tools and visualizations. Well, and then now AI and DNN, I think that the difficult part is that this is a very, very just useful tool, but very difficult to sometimes understand, align, or use. And then I think this is the challenges that we are encountering. So just briefly introducing myself again, I'm a lover of human. I prefer to represent humans than the technologies when I do the research or designing. And because of that reason, I do really believe that the formative study or understanding humans before we actually just like move forward is very, very important. And as Eun-kyung said, I'm a newbie in information science and technology at George Mason. Just started, things are crazy, but I'm just really happy that I can land in these beautiful areas and then work with a lot of great creative people. Well, and I decided to work on the human-driven HCI and CSW research. And then my main focus is the alignable AIs, which Eun-kyung briefly said. So the problem of these AIs, and especially deep neural network, is that there is a little bit of uncertainty, or sometimes just a huge uncertainty, that people cannot really grasp what will going on, what will happen when they're just like working with the deep neural networks. And then I guess one of the missions that we really have to achieve is that presenting the interactive modality that enable people to adjust, regulate, steer, or use the AI based on their just meeting with their just like expectation and the mental model. So in doing my specific research, I have three project directions. Like first direction is the interactive data annotation. Well, the good model comes from the good data set. And then this is basically happening in the like crowdsourcing environment in many cases, help data scientists to more or less efficiently collect and update the data set that can accurately represent the target population of interest. And then the second part is the interactive model building, which I think is pretty my main focus nowadays, and help data scientists to better understand and steer the deep neural network model. The last one is the AI-powered application. Now that we have the model, and then so what? What can we do with this model? Really just, professional environment. What can be the design principles or the design of the tool that can really make the difference of their life? So those are my main just three directions. And today I'm gonna briefly just talk about my main project in topic 1, steerable deep neural networks. And then topic 2, supporting digital colorization for professional web comic artists. Those are two main projects. So we'll just like start from the first project, but before we go, this is something that I want to just like briefly talk. So myself, I'm the first year junior professor, and I really want to get some feedback from you in terms of my kind of directions can be interesting. What is the critiques that you have? What can be the related work that I'm missing? That type of thing. Is the scope of the research reasonable, or this is too broad? You guys have a way more experience than me, so I would be happy to have those comments from you guys. If you are just searching for the research partnership, yeah, this is something that I really want to achieve. If you're interested in the research collaboration, we could schedule a one-on-one meeting after the presentation. So feel free to shoot me an email. Yeah, I wish to just talk with you guys as much as possible. So I hope this can happen. And if you're a student, and then if you're also just looking for the summer internship, and then if you're the PhD student, of course, your advisor has to agree on. But I'm just also hiring the summer interns during this. So if you're interested in, and then you can also just shoot me an email. Okay, so let's just like start from the topic 1. Topic 1, aligning the eyes between the humans and model, steering deep neural network using interactive attention mechanism. This project is just collaboration with Emory University in Liangzhou and Yuyang Gao, and then my PhD student, Stephen Sun. So many say that one of the amazing examples that demonstrate how machine learning can shift our way of computing happened in early 2012 in Kaggle. A team led by Geoffrey Hinton from the University of Toronto just won the competition of automatic drug discovery. And then now what was extraordinary here is not because they beat all of the algorithms developed by the world-renowned experts in the academic area, but nobody in his team just had any background on chemistry or biology or life sciences, yet they made their algorithms just 2 weeks, and then they won. So what did they do? How did they do it? So I guess this is a very easy question. Anyone? Okay, well, it's easy. It's this topic. They used a deep neural network, and the success was covered in the New York Times a week later. And well, so in fact, in early 2000, we started having the machine learning model that can do better jobs than human. So for example, in 2011, we had the first AI that can better recognize the traffic signs than humans in a competition called German traffic sign recognition benchmark. And in 2012, again, the Geoffrey Hinton won the popular ImageNet competition, showing AI can better figure out the objects in the images than humans. And well, 2016, this was a pretty big event. AlphaGo won Lee Sedol, the world Go champion. And then I felt sad because especially I'm a Korean and I just was like slightly into the Go. But the bright side of this is that this event made a lot of people seriously thinking about the implications of living in the world with the deep neural network models. So, well, now because of this kind of the powerful deep neural network, demonstration of the powerful deep neural network, people now started to deploy these deep neural networks. But I guess the problem is that it is actually very difficult to build a nice deep neural networks that works exactly as we think. So Janel Shane is an optic research scientist, and then he collaborated with a couple of people and collected the 1,600 types of different ice cream flavors around 2010. And then they just made like a model and then just tried to make some predictions in terms of what can be the mind-blowing ice cream flavor. And well, you can see the first one is the pumpkin trash break. Well, the second one is peanut butter slime. And the third one is the strawberry cream disease. Well, yeah, it's not that easy. Actually, well, this is understandable. They are not really just professional, machine learning engineers, but still almost every of the machine learning engineers, when they try to build a machine learning model, especially deep neural network models, it's not going to be very just successful at the beginning. And then they have to do a lot of tuning and then fine tuning. And then sometimes it's very difficult to adjust because they don't know how this works in the back end in the end. Well, this is the formative study that I conducted when I was in New York University, working with Jessica Holman and Enrico Bertini. So we just did a lot of interview with the field research scientists and data scientists who really just, work on the production line of the deep neural networks or some AI models, and then especially interested in model interpretability. I think that they really wanted to use the deep neural network because of this state-of-the-art kind of accuracy, performance, and the good kind of capability. But most of them just concerned that they really want to use this, but they cannot use this because of this unintelligible nature of the deep neural network. So this is actually happening in the world still, surprisingly. People think that we are just using the deep neural network every time in every cases, but actually that's not, especially if the industry is regulated industries such as bank or maybe health industry. So from my perspective, those issues are related to the DNN's lack of intelligibility. We cannot really understand the global logical structure that deep neural network rely on in making the prediction. And then also the alignability. We really cannot understand how to intuitively and directly fix some of the failures based on their observation. So I guess these two are the main problems that I really wish to just tackle. And then I think that the human factor research, we have a kind of good hands on this. So today, my kind of first research direction that I want to introduce is interactive attention mechanism. And like, what is this? This is the pipeline that we are proposing in some conference. And basically what's going on in here, I will just like try to explain this one by one, but you can just divide this pipeline into the two parts. So the first part is to focus on understanding the model, deep neural network models, in terms of when it fails. We want to understand when it fails. And then depending on when it fails, we can just collect the instances that fail and then use human attention to adjust that and then feed that into the deep neural network's fine-tuning process to fix that. So the later part is about how to fix this. And in that way, people can more directly and then intuitively indicate their ideas in terms of adjusting the deep neural network. So let me go for the first part, when it fails. So conventional way of assessing the deep neural network or the machine learning model in general is we use the prediction accuracy. Was the prediction accurate? And so, for example, if you are talking about the gender classification, let's say that we have two images here, and then the instance, the model, deep neural network, convolutional neural network, classify this as a male. And then that means that both are accurate. So that's the first question that just people use whenever we assess when the model fails. And my approach, we want to include one more question. So the attention given to the instance is reasonable. Nowadays, because of these interactive attention mechanisms and then the explainable AI in deep neural network, you can easily understand the part in the instance that deep neural network rely on when they are making the prediction. And then I want to suggest to use this attention layer as a way to understand the success or failure. So for example, if you see the two images and then we have the another kind of attention images that just screened out the other part, but just only show the areas that the neural network is focusing on. In the left-hand side, it predicted this as a man. And then the reason that this deep neural network predicted this as a man is because it saw the motor bicycle in below. This can be reasonable or not reasonable. It really depends. If you think that only the men can ride the bicycles, then this is reasonable. And this is not reasonable if there's a case where a female can also ride the bicycle. So in that sense, I think this is just like not really just good type of attention. But on the right-hand side, the model just really focus on the part, the human part. And if you see there's some contextual objects such as skateboarding or some kind of background objects, but model doesn't just pay attention on that. So I would say this can be a reasonable attention that really focus on the human part. So by including one more question of whether the attention is reasonable or not reasonable, we can build a reasonability matrix that specify any instances within the 4 category. So first one is accurate prediction or inaccurate prediction. And the second one is the reasonable attention and then unreasonable attention. And then we can just establish these 4 kind of layers, 4 categories: reasonable accurate, unreasonable accurate, reasonably inaccurate, unreasonably inaccurate. This can be slightly confusing. So let me just like go some example one by one. So let's say the neural networks classify this as a female. And then if you see the attention, attention is really given to the part of the human body. So I will say this is reasonable. So this instance has been predicted accurately, and then the instance that has been given to the image is reasonable. Now let's see the second one. This is the neural network predicted as a male. But if you see the attention, now the attention has been given to the bicycle, which I think that woman can also ride. And the reason that this instances has been predicted as man is because it saw the bicycle. So this is accurate, but unreasonable in terms of attention. So this is unreasonably accurate. So the third one is now reasonably inaccurate. Attention has been given to the reasonable area. It's a beard. But for some reason, this model just predicted these instances as a female. Maybe there were not many data points similar to this type of instances. Maybe that can be the reason. So the last one is that now this is unreasonable. Attention is given to some contextual object, not the human part. And then the model also predicted this as a male. So it's inaccurate, and then attention has not given to the right area. So this is unreasonably inaccurate. So, well, by doing that, now we can actually classify those 4 categories in any instance that has been used or predicted. Then now, how to fix when this case happens? Now, this is the later part of our attention mechanism. So first of all, for the instances that didn't have the right attention areas, we built a user interface that help people to adjust the attention. So for example, you can actually circle the area of the lady's head instead of the other parts. and then maybe just feed this to the model. And then by this way, we can collect the instances with the right attention or reasonable attention. And using this attention, we can actually adjust the attention. We can actually fine tune the model. And then the part that you may want to focus in here is the two parts. Well, so now we have the images, and then now we make the model, the classifier. Then classifier will predict this is a female or male. But if this is wrong, and then we will have the prediction loss. And then there's the attention that has been derived by the ReLU. And then now we collect, if this attention is not right, then just now human annotator will just like draw the line here. And then now we'll just compare this attention map and then this line, the ground truth attention, and then we'll just like calculate the attention loss. And then this attention loss will be used in attention backpropagation. And then this precision loss will be used in accuracy backpropagation. And then we jointly just like, max this in fine tuning the model. And then now the result will come. So this is the object functions that we used in interactive attention mechanisms for steering deep neural network. And as you can see, so basically we are using the loss for the prediction. And then this comes from the every instances that is inaccurate, unreasonably inaccurate, or reasonably inaccurate. And we also consider the attention loss coming from unreasonable attention, unreasonably accurate, unreasonably inaccurate. And then R is the scale factor used to balance the prediction loss and attention loss. It's just like depending on the situation. So I just briefly introduced our interactive attention mechanism pipeline and also the Gradia, the tool, the name of this function, and then our core of fine-tuning the model is named Gradia. So I think that we have to have a fundamental question, why we have to do this. We just like, if we do this additional work, to see all these instances and then check if this is reasonable or not reasonable. And then if it's not reasonable, then I think this is the right attention area. This is a lot of work still. So is this still effective? So that was the first study that we wanted to understand. We wanted to understand whether establishing the reasonability metrics in fine-tuning the model can be actually useful for improving the deep neural network's quality. That was the first study. So this is the study setting. We used the COCO dataset and then fetched the 5,000 images, 2,500 women and 2,500 men, so 50-50. And then we sliced this data into the three parts. First part is the training set. 70% of the images, 3,500 pics, 1750 like men and women. We used this training set to train the base model. So we have the base model now, and then the base model has been built using ResNet 50. Then now we used a validation set, which has a 750 pixels for men and women to build the reasonability metrics. So basically using the base model, and then we actually predicted this and then just check the reasonability and then just try to establish this reasonability metrics as 4 type. Right, so we have the accuracy for sure after we use this ResNet 50 base model. And then now human annotators will go over 750 pixels one by one and then check this is reasonable or not reasonable. So now we use the validation set and then we build the reasonability metrics. Now, this reasonability metrics will be used for building the 4 different types of model. So the first model is the baseline model. We don't use this attention loss at all, but we only use the precision loss. This is the control 1, the baseline model. And well, there can be some case we don't even just build the reasonability metrics, but just use the inaccurate instances to adjust their attention if necessary, and then train it. In that way, we don't have to go over 750 images one by one to check the reasonability metrics. Just fetch the inaccurate instances and then just change their attention and then just retrain, or I'm sorry, just fine tune. So that's the also the inaccurate. This is the second condition called inaccurate. So basically we collect the inaccurate and then change the attention. Now we have the 2 experimental conditions. The first condition is unreasonable. We build the reasonability metrics still, and then we adjust every of the unreasonable instances here. And then the last one is the full. Now we change every attention and then every inaccurate instances. We fully use this. So basically, this is the cheapest, this is the second cheapest, this is now a little bit heavy, and then this is the heaviest condition. So it needs more human effort as we go by. Well, we just use these 4 different models and then evaluate this model using the testing data set eventually, which has another 15% of the images, 750 pixel. This is testing set. So let me show you some of the results. This is just basically the process that the team already did, eyeballing, if we can just find some differences in general. So we place the images and then see the differences. So if you see the baseline here, this is kind of very obvious case. A baseline, the attention is given to the bicycle, autobicycles, automobile. But as we goes to the inaccurate, unreasonable, and full, now attention is slightly moved to the human part. This is slightly subtle. It looks similar, but actually there's a contextual object of surf. And then baseline, actually, it includes a pretty just obviously there's a surf, but now if you go to the unreasonable and full, the attention has been focusing to just the human, for example. Well, this is this is the case where the full is actually worse than unreasonable or inaccurate, because there is the surf, but then the inaccurate and unreasonable shows the better instance. And this is also very obvious instance. Now lady is playing the tennis, and then baseline and inaccurate pay the attention to the ball or the tennis racket, unreasonable. But I think that the full really just captured the human part well. Some more examples. Well, baseline. Generally, you can see the baseline is has a more scattered attentions than the rest of the 3. And then as we goes to from inaccurate to unreasonable to full, now we have the more focused attention. That's kind of the research that we use the Gradia. Well, here, for example, we can obviously see the elephant in baseline, inaccurate, unreasonable, but in the full, you can only see the guy. Not only, you can just slightly see the elephant, but compared to the inaccurate, unreasonable, this is way, way narrow. So something like that. So this is generally the kind of research. So we thought that maybe this can just see the differences, so we decided to run the study. So we did a couple of measures. So the first measure is the computational measure. And then of course, the precision accuracy is still the most important, quality measure. Another one was IOU, the intersection over union between model-generated attention and human-generated ground truth. That means that now the model gives the attention in this area. And then now we actually just made the ground truth for every of the 700 images. We just tried to measure the overlap between the model's generated attention and our ground truth for basically this testing set. So here's the here's the research about those computational measures. Well, so great part is that we just adjusted the attention, and then sometimes people think that if we actively involve in just manipulating the model's behavior, that can just go against on the model performance. But we didn't see any actually just performance decrease. Actually, our full was the highest, which is interesting. In terms of IOU, we can obviously see that the baseline is the lowest, and then as we goes to the full, it goes better and better. But I think that the decisive battle doesn't come from the computational measure. I think the humans has to really see the quality of the attention has been increased. And then I think this was the more important measure than the computational measure. So this is the human assessment based measure. So we try to measure the 2 different things. The first thing is the reasonability. So now going through the 700 images again, and then check just elicit people's labeling in terms of, okay, the attention was reasonable or not reasonable. And then just if some model has a better reasonable kind of instances than other, that means that the attention has been improved because now this is reasonable. The second part is the perceived attention quality based on the criteria of this attention, correct? Based on the quality, perceived quality, we just actually ask people to measure from 1 to 5. This is the good attention to the bad, the worst attention to the best attention. So this is the way that we collected whether the attention is reasonable or not reasonable. And then the way that we collected this reasonability was giving them some 2 questions for the 4 conditions. So the first one is that, does the focused area contains the necessary detail that help you to classify the gender? So that means that if you see the attention, that you have to really understand whether this is male or female. The second part of the question is that does the focused area contains unnecessary contextual objects not directly related to the gender classification? That means that if there's a snowboard, or if there's a car, or this is a baseball, then that's not meeting with the second criterion. So the way that we measure this is reasonable or not reasonable is that if they answer the question 1 as yes and the question 2 as no, then this is reasonable. And that was the research. So we just run the Kruskal-Wallis H test to check the differences between these 4 conditions. And actually, every condition has been significantly different. Baseline was the worst, inaccurate was the next, and then unreasonable is the best, and then full and unreasonable, actually there were no differences. So, so that means that if we are applying this interactive attention mechanism and then build a reasonability metrics to adjust the attention, then it will be better than baseline or just using the inaccurate. So that's the first research. And well, the interesting perspective, we just try to just like make some heat map for each of the model in terms of how they answer the 2 questions. So if they answer the first question as yes, yeah, we can just see the necessary detail. And then no to the second question, there was no contextual information, then now this is a reasonable attention. If the people say yes and yes to 2, there is the required attention, but still there was also contextual attention. This is the surplus attention. If they just say no and no to everything, that's weird. There was no detail that they can just use to predict, classify the gender, and also there's no contextual object. So there's no attention, almost. So this is insufficient attention. The last one is just saying no and yes. And if they say to the no, the first question, that means that they cannot actually determine whether there's a man or woman, but they can actually just see some kind of snowboard or something that's very contextual, that this is really contextual, the bad case. And if you see model 1 was baseline, this is inaccurate. The third one is unreasonable. The last one is now full. We just consider everything. And then basically you can see here is that now there was like 339 instances that was in the reasonable attention, has been increased with 612, so almost double size. And then if you go to the model 2 and model 3, you can just see the more reasonable attentions growing up. And in terms of, but the great part is that, that's good. But the interesting perspective is that now even the model, so the full model, there's like the biggest reasonable attention. Some interesting thing is that still there's the more, if this attention is correct, there's like more inaccurate instances, 94 instances. But if you see here in the model 1, there was only 33 instances. So that means that if you're just going to the model 4, which is full, well, the quality of the attention is increasing, but still accuracy-wise, especially in the model reasonable attention, they may likely to include some inaccurate instances. And I think that's because we remove the every contextual information, attention, but just if the human part is very small, then maybe this can be not enough for model to make the prediction. Maybe that's the reason. And then in that case, I think that we need to do some further kind of stuff to increase the accuracy. But that was kind of interesting finding. But anyway, so really just the important finding in here is that if you put more effort, then you will likely to have more reasonable attention. The second part was the human-based quality assessment, and this was the screen. There was 4 conditions. Everything was randomized, so people cannot see which condition is where. And then we asked people to label from 1 to 5, very poor to excellent. This is the results. More or less, this is same with the reasonability question. So C1 was the lowest, and then the C2 was next, which is inaccurate. C3 was unreasonable, and then C4 was full. And every pair was significant. That means that if we are just putting more effort, then you will likely to have a high quality attention from the labelers or the human's perspective. So more or less, so interesting perspective that we found in the first study is that we didn't observe any trade-offs between the prediction accuracy and attention accuracy, which sometimes people say. If you adjust model's behavior, intervene, and that may hamper the model's prediction performance, but we didn't actually observe that pattern, which is good. And then we were able to observe the significant improvement of the model reasonability, especially when we are applying the reasonability metrics. So go over the instances and then check whether this is reasonable or not reasonable. And also, especially, we just actually apply the attention loss in just fine-tuning the model. So the ranking for the computational quality of attention was the baseline was the worst, inaccurate was the next, unreasonable was the third, and then full was the best. Unreasonable and full, there were no differences. So unreasonable and full is pretty good in terms of IOU, but the ranking of the perceived quality of attention in terms of that, full was better than unreasonable. So I think that the message is pretty simple. If you use this reasonability metrics in general, and then you will likely to have the better results in terms of attention quality from the human's perspective. This is the general finding in study 2. Now, well, so let's say, okay, it is good that we understood if we specify the reasonability metrics, then it can improve the quality of the attention. But what about we comparing our gradia to compared to the state-of-the-art attention adjustment methods? So we just tried to look through the literature, and then the one that we found was attention branch network, which has been suggested in 2019. And I think that this paper is also very interesting, embedding human knowledges into deep neural network. And you can see there's an initial attention, and then there's a human expert, and then they're adjusting their attention, and then now the attention is moving. So that's kind of their approach, which is pretty similar. But the difference is that they are actually adjusting modifying the base model, but we are kind of using our model as like a filter. So let me just explain this further. So we just try to compare the study 2. Our goal is to understand whether gradia can be better in terms of perception quality or the accuracy quality than attention branch network. That was the question. So we prepared the same data set, just like the first study. Well, so we built the first one, the ResNet 50 is gradia based. We'll just use this ResNet to build the gradia, which I think is pretty similar to study 1. And then the second one, in order to use the ABN, now we have to adjust the ResNet 50. So we adjusted the ResNet 50 with the ABN. Now, and then we did some same thing, but now we have the 2 different models here, right? So in using this validation set to establish the reasonability metrics like this, we just like did the second, the different like step, separately, we just build the reasonability metrics in a separate process. So ResNet, we build the reasonability metrics, and we found 295 instances unreasonable out of 750. And then using the ABN, we found 433 unreasonable instances out of 750. So the number of unreasonable instances is different between the gradia and ABN. So that means that if we have to adjust more attentions, that needs some more effort. So we wanted to specify the conditions like this. So ABN basis baseline. It's just based at ResNet plus 50 plus ABN, but we actually don't adjust the attention loss in just fine tuning. It's a baseline one. ABN match is that now among the 433 instances, unreasonable instances, we only use the 295 instances, so that the effort that we made to adjust the model is same with the gradia. The third one is the ABN full. Now we use the whole 433 unreasonable instances in updating the ABN. The last one was Gradia. We used the 295 instances to update the model. Well, this is the results of the study too, in general. So this is the original images in here. And then the second column is ABN base. Third and fourth is ABN full and match. Now this is ABN kind of approach. The Gradia is the last one. So the interesting perspective that we found is that if the ABN base is the showing, presenting the attention in some irrelevant area, such as here, you see the attention is given to the wheel. And then now ABN full or match just goes well. They're just directing towards the human better. Like here, I think there's some examples here. There's like the shirt, but now just moving to the human's face. Well, now this attention, if you see their horse attention is moved to the human, for example. But the interesting perspective is that if ABN show the instances in the right area or reasonable area, now the attention tends to scatter whole across the screen. That was the interesting thing. For example, here ABN base, it actually focused on a human here, but now it's just like moving all around the space in these images. So I guess that was like something that we found interesting. So I think that if we are using the ABN, then it tends to broaden the attention for some reason. And then Gradia, I think that we really just make some very constrained and then just focused attention in general. Well, it's not everything. It's just a kind of the instances that we pick. So, but we kind of thought that maybe, okay, there can be some differences. So now we are working on the experiment. We are still working on the experiment. There are some results still. So I think that the measure was the same. For the computational measure, well, prediction accuracy, the great part is that Gradia was the best. We didn't actually just see any difficulties in also increasing the IOU. I guess the reason that the Gradia was achieving the highest prediction accuracy and IOU was because our objective function, we just try to balance and minimize the attention loss and precision loss. We are just like balancing this, and then just we tried a couple of different scale factor, and then just I think that was the results of that. I think that the really important part, this is not just confirmed yet. We are just still collecting more data. But so the reasonability performance, people think that the 73% of the ABN is reasonable, and then it goes up to ABN match and then full and Gradia. So ABN match is worse than ABN full here, but both are slightly less than Gradia. So that's one perspective. But the interesting perspective was the perceived attention quality. Well, if you see ABN full, we use more instances to fine tune, right? And then reasonably performance is better here. But for some reason, when we are asking their perceived quality, this was less than ABN match. So we use more effort, but their perceived quality was less than ABN match. And how bad it is, it was actually worse than ABN base. So I think if we are just like feeding more instances in ABN, and then sometimes it can just scatter the attention, and that makes people feel this is not a good quality attention in general, which can be the threat. So this is the perceived quality of the attention for the 4 conditions. You can see ABN base and then ABN full or ABN match. This should be ABN full. ABN full is kind of, like similar, but ABN full is slightly less. ABN match is slightly better, but the 3 conditions are less than Gradia. So the interesting perspective, again, we didn't just find any trade-off between the precision accuracy and attention accuracy. So more or less the baseline and then attention adjusted condition, they just show the similar attention precision accuracy. And then as I briefly said, the ranking was different between their reasonability accuracy and their perceived quality. The interesting part was that ABN full was the worst. So I guess that what it means is that we have to really understand what can be the sweet spots that doesn't just make the ABN just okay. What is the term? Well, so the right amount of the size that can just like maximize the performance of the ABN. I think that's something that we really have to understand later on. So, well, this is just very crisp approach that we just try to do the interactive attention mechanism. Well, I guess the design rationales in here was that, well, if we kind of find some instances that doesn't really fit into my kind of ideas, this is wrong. The instance has been made on wrong kind of, like explanations, tension. There was no way to directly update this. So the way that we have to adjust this deep neural network is generally we have to do some like parameter tunings or some more indirect way. And actually the kind of the research that gave us the motivation was the direct manipulation. It's metaphorical, it's not actually direct manipulation. But I think that we have to have more direct way to interact with the deep neural network to improve the way that it behaves. So this is kind of the underlying kind of enthusiasm in this project. So this is a couple of directions that I really want to work on in the future. Well, building the reasonability metrics, I just like did it for 750 once, just try to understand how hard it is. It just like gave us, it made me just spend more than 3 days. It was really hard process. It's very labor intensive, but I think that there can be a lot of great intelligent interaction features that can really boost this process. This is so manual, and then just like going through each of the images and attention one by one, and then check this is reasonable or not reasonable, is not cost efficient at this moment. We have to improve the way that we specify the reasonability. The second one is that, well, as you can see, we don't have any interactive system. We are saying this as an interactive attention mechanism, but I don't think this is truly interactive. So we have to really find a way to make this tool more interactive than now, so that maybe we have to work on some approach for visual analytic systems or something that we have to just do. We have to just improve the computational pipeline. We have to immediately see if I just change this attention, then how this instance attention can change. I think capability of this interactivity can actually benefit people in the future. Well, and then the Gradia itself, I think this is in a very early stage, so we have to improve this. Well, so the next part is that now we were mostly applying this interactive attention mechanism in the debiasing, the gender classification, which I think that the contextual information is considered as detrimental. But contextual information can be actually very useful in different application layers. For example, if you want to make some prediction classifier for their kind of emotion, then I think that now, well, just focusing on their head will not gonna give them a lot of ideas. We have to actually just like, grasp the context. Now, she's a winner in an Olympic or something. Or if you're making some prediction model for classifying very fine detailed kind of species of bird, then I guess the different types of attention should be given. So the way that we direct the attention should be application dependent. It's not that contextual attention is bad or intrinsic attention is good. We have to really understand how we can actually query the right way to adjust the attention in the future, depending on the application areas. Well, and then I think that the attention can be really contextual. I think that this is a very cool project, visual common sense reasoning. And then this project actually explains why this person 4 pointing at person 1. Well, and then there's a reason for this. I think this is a very cool project I really like. This is all about context. There's all about context. There's no, just all kind of, the common sense can be very just like, mild term for bias in general, right? Well, people just think like this way, so that you have to think like this way, right? But I guess in this way, what should you do in interactive attention mechanism? So applying this visual question answering problem in attention mechanism can be very different from what we are doing. The last one is that this is something that we have done and we are keep doing. We want to adjust this attention mechanism to graph neural network, and then there's a lot of application areas in this graph neural network, such as scene graph or some like a chemical formula classification. Well, I'm a little bit afraid I don't have a lot of time, but I'll be happy to listen to question, give you the question. Any questions so far?
Hi, everybody. Young Kyung is going to help moderate the questions, but I do have a favor. If you would consider coming on screen and showing your smiling faces, this is one of the reasons we do have the brown bag lunch, is to get a chance for us to all reconnect since we haven't seen each other in a year. So I love seeing you all. And Young Kyung, why don't you go ahead and field some questions?
Sure. Well, thank you for the talk. Let's see if you have any questions from the audience. You can raise your hand or put your question in the chat window. I can start. So I have some high-level questions about the context of this Kyoku data set and the focus of your work. So there's this notion of gender and different notion of sex, and I'm trying to understand what you're trying to predict, whether it being sex, which is usually female, male, and in other slides I saw that you're focusing on gender, woman, man, and there are also gender non-conforming types.
Oh,
So,
sure.
and can you explain a little bit about the nature of Kyoku data set and what ground truth data they have and what you're trying to predict?
Right. So actually, this is not maybe gender classification. Sex classification is more suitable. This is the term actually. So based on the appearance, we kind of just see this is a female or male. So I think this is more suitable for sex classification. The reason that we wanted to do this problem space was that the data set itself is easy to get. The COCOS data set has the more just very rich kind of ground truths in terms of like, you know, the people inside in here, and also how many people are there. So that was very helpful for us to actually just select, for example, some images likely to have some contextual information. Like, so for example, a woman's in the kitchen, for example, or men in the like snowboard, kind of, or something like that. So that was very easy kind of, you know, data set that we can collect with a more kind of, you know, context. So which was the good settings for us to test this thing. But thanks for the clarification. I think this is a little bit tricky problem, especially in the Chi community, because gender, sex is very subtle and then very complicated problem. The reason that we just focused on this data set was because this was still very approachable and accessible data points that we can leverage in working on the interactive attention mechanism.
Okay, thank you. Let's see. Any questions? Hernisa?
Yeah, great. Thank you for your talk, Ray. And I want to echo Young Kyung's also questions. Or, you know, perhaps some of the problems could have been a little bit more away from things where actual people are supposed to make inferences on other people's gender. But another follow-up question on that was, I see how you envision this for computer vision systems, the attention. Do you have any insights for models where there are not images that people can point, like to be, you know, classifying our activities, for example, or classifying speech? Like, how would you imagine the attention from humans going back?
So yeah, that's a very good question. And then we are, again, just very interested in extending this to graph neural network. For example, even if this is a very just simple network, the amount of information that the network contains is very complex. And then like we can actually just specify the attentions, the weight of the attentions in the network. Okay, so this is the toxic formula or not non-toxic formula. And then depending on this attention quality, maybe experts can see, oh, the model predicted this is non-toxic, but because of that area, this is toxic. They can adjust then. And then this can improve the attention quality as well as the prediction accuracy. This is just very short applications that we can consider. I'm just also just trying to think about recurrent neural network, but this wasn't very easy so far. We are just like trying to just working on it, but I think that the more close one is graph neural network at this moment. Thank you for the question.
And we have a question from Susan Campbell. Do you wanna?
I can read it if you prefer. I just wrote it down because I wasn't sure how we were doing Q&A. So, I'm a psychologist. We know that people don't necessarily have the best idea of what cues they're using when they make a judgment. And so I was kind of wondering if you could expand on how that might interact with the idea of having people pick out parts of an image, right? So, they might actually be using the motorcycle even if you tell them not to, right? So how does that interact with the system?
Right. So I think that you're talking about the human subjectivity in terms of assessing the reasonability of the images in general. And this is actually very true. I think that what we just try to do is to make their decision making in terms of reasonability as crisp as possible by just giving them some very explicit two criteria. Can you just specify, recognize the sex in this sex of the figure in the images, or do you see any contextual objects? But if the task is becoming more complex and a subject, I think that now it's becoming way, way difficult than what we did. Maybe if we are just doing the multi-class classification, for example, with more subtle kind of differences, now then we have to really go with maybe rule-based, very just crisp way to do this. So even just asking people to check the reasonability, we had to specify this to the two questions. We couldn't actually, we were a little bit afraid if you're giving the one question, is this reasonable or not reasonable? And then people are not going to be able to answer as we kind of expected or we wanted. So yeah, I guess operationalize the complex question, very just sliced information and question will be very, very important for eliciting this information from general people. And thanks for the question. Yes.
Thanks.
Next question is from Shihong Chen. I can read it. Do you expect your reasonability annotations to transfer to other attention models other than ResNet? So do you think the same images will be unreasonable across different architectures?
Yes, so Gradia can just do that, but ABN cannot. As I said, basically this is the model architecture. Gradia can be considered as more as a filter, so that you have the attention loss, and you have an adjusted attention that you can just apply to different models. The ResNet ABN itself, I think that it has just be combined with the base model. So that was one of the selling point that we wanted to make in the submission in terms of why Gradia can be more adjustable and then applicable to the broader model basis. Yeah.
Thank you. Next question is from Yali Bian. Can you talk more about the step 3, how the fine-tuned model with attention loss can boost professional workers' productivity?
Yes, I hope that I have a time to do that. Yeah, but can I do that? I think that we are almost just using up our time. I think that I can just do this for 5 minutes, for example, if you guys allow.
I have a suggestion.
Sure.
I'm going to do some closing remarks, and just so that everybody that needs to get on with their day can, and then anybody that wants to stay around to get the answer to that. Because before everyone leaves, I want to take just a minute and share my screen. Excuse me, just 1 second. And do a quick promotion for the upcoming HCIL symposium, May 27th. We've got a nice program already planned. You can go online, 2021 symposium, and you can see all the sessions we have. And so, for example, if you look under Young Kyung's session, social media, visual analytics, and health, she's got 5 different sets of presentations. So here is how you register, super easy. But the other thing is I will be sending a call out for volunteers. It takes many hands to put this together. So far it's been a one-woman show and I cannot do it all myself. So I would very much appreciate some volunteers. So I just wanted to say thank you, wanted to make that plug. And then Ray, go for it. Go ahead and give your answer.
Sure. So does that mean that I can just keep going? Okay.
We can keep this room open for a little bit longer, but for those who need to leave, well, you're welcome to do that. But I also want to give a shout out to Ray Hong for giving this nice talk. And also, he is a new-ish faculty member at George Mason, and he is actively looking for collaborators and student interns for the upcoming summer. So feel free to reach out to him, and he's our neighbor at George Mason.
Yeah, I'm happy to be a neighbor.
So thank you, and yeah, go ahead.
Okay. Yeah, I guess the first one was a little bit heavy topic. The second one is pretty fun. Now, let's talk about how we can just support more professional people using the deep neural network. This is the collaboration with George Mason University, Yotam Gingo, and then Chuan, and then University of Michigan, John Junyoung, and then Idan Adar. We are the great team. I kind of think I think this project was very fun. Okay, so nowadays, if you're just seeing the webtoon, and then generally the webtoon is all colorized, it's very different from the previous printed medium, right? So everybody just colorize them, and then they just make this product. Well, so and then the digital colorization is not that easy. It's a very labor-intensive process, and then the idea of using this AI-driven digital coloration in the wired has been just out there for a long time, and it pretty much looks like it's promising, right? So if this is kind of example of the images, and then just a AI-driven digital colorization. In the left-hand side, you can just like make some brush like this, and then in the right-hand side, there is a research. What do you guys think? Is it a good kind of good enough? You want to use this? Well, I guess well, answer is no, unfortunately. So if you see the detail, there's a lot of miscoloring here, and like for example in here there's a book, and then just like color in here. I even just specify I want to just put this in the red like this in the brush, but it still just make this blue. The strip makes the color between the below and up very different. If you see there's like a small kind of slight hair that should be yellow, it's red, but you cannot actually change this. So all this perspective just like giving the feeling that the digital artist is not controllable. Well, actually, and then also if you see those images, it's very blurry. If you see the line drawing, there's still just crease line. But if you apply this deep neural network in sometimes, then now that makes kind of blurry effect. That's kind of indispensable. And if you see the really just like product level of, production level of contents, then now this is very crisp and then very clear. Every line should be distinguishable, and then just the thing should be very, very just like alive, right? Not like blurry. So one of the papers that I really love, it has been presented in CHI, I think 2 years ago, somewhere there. Automation accuracy is good, but high controllability may be better. For supporting the people like professional cartoon artists, they really have to have the control, super control, because that's kind of the thing that they have to just make the product. If they cannot just like make even single line and then change the color, they cannot make it happen. They cannot just use this. And when we are applying this DNN, the DNN is absolutely a useful tool, but often cannot really support the professional experts in the wild because of the controllability. Is also related to their unintelligible nature and unalienable like nature with the human mental model. It's very difficult. So our overarching research question in here is, of course, we want to help digital cartoon artists, but how can we update the DNN as a productivity tool that can really support the digital colorization? So that was our kind of research question. And I think that one of the best practices in the HCI, what should you have to do? We have to work from the formative study. We have to understand what they do and then apply our technique. So we just started just doing the formative study. We met the web cartoon artist, and then just like, did some interview one by one. They just tried to generally understand their workflow, what types of, the steps that they're just getting into in order to create the digital colorization. And then what challenges that they just encounter whenever they use their tool to do the comic colorization. What is their general perception about applying the AI tool in their workflow? What types of specific features that they wish to get help from the AI? And the factors behind their intention to adopt the AI-based tool. It's just more or less kind of our goal in this formative study. Well, and then we just did some 5 interviews, and then interestingly, they did pretty similar thing. Their workflow was very same. Their perception was very, very similar. Their type of the tools that they wanted to get was also very, very similar. So we were able to saturate ourselves pretty well within even just 5 people. So this is the results of our qualitative analysis. But the first thing that we were able to identify was their workflow. So it looks very simple, but actually there is a formalized steps that the digital cartoon artists just follow when they're just colorizing. So the first one is that they have to prepare the line drawing. Then the second, they have to do what they call flatting. This is basically base colorization based on their human semantic. That's the tricky part. I will just talk about this a little bit further later. Then after they finish this base colorization, then now they're adding some more detail by adding the shadows or the lightings in this base colorization. Now, then after that, they just do the backgrounding. They're making some background. And then now after that, every background is there, and then just the color is there. Then now they're including some special effect. And then later on, they add the text. This is appearing to every of the people who we interviewed. And the interesting part was definitely the flatting. So flatting is the process for the base colorization. This is the line drawing in the left-hand side. And then now the flatting is the results in here. You see there's no, just like any of the lightings or the shadowing here, but just the flat colorization. And then if you combine this flat color with this line drawing, and then you will be able to get the results like this. Still, flatting is a very important process. But the really interesting part that we found, I'm going to just show you the video in terms of how they are just doing this like flatting.
Flatting, I'm going to show you the correct way to do it, or a correct way to do it. I know a lot of colorists have a hard time finding and keeping good flatters. So that's what this video is going to be about. And if you don't know what flatting is, we'll kind of wrap.
So as you can see, they're basically drawing those lines manually.
I'm going to show you the correct way
based on their semantics. So for example, this head, and then this next should be the one base color. And then now this hand will be another color. So color this, and just like, do more and more. So this is actually 19 minutes of video, but just what they do is just two sets of colors, two sets of like the images with this flatting. And what was very surprising was that this is very, very manual. They're just, exactly just like following the same like line drawing, and then make the base colorization, and then move forward and move forward and move forward. So, okay, so after they finish this flatting, now they're including some shadowing and lighting. Sometimes this is monotone. Sometimes they're having a few multiple tones with a very deterministic definition, such as here. Sometimes they're applying the full gradient, just a really, really full gradient in just like presenting this shadowing and lighting. Well, then I think that the backgrounding is that they generally don't do anything on the backgrounding. This is largely asset driven. That means that they're going to market and then buy some background and then just put this in the back end of the humans or the characters or the object that they drew. Now, the last one is the special effect. You make those images and then make some like really just special lighting effect or some, like awesome effects. Then adding the text, that's it. So basically, what we have found in here is that there is a few different steps here, which they just like distinguish one by one. And then depending on their step, their perception of applying the AI was very, very different. And then flatting was one of the best steps that they really wanted to get help. So basically, they think that the process is very repetitive, laborious, and then sometimes they have to hire people in order to do the flatting, and then they're perfectly fine with this because they don't have a lot of ownership. That means that like, who can do the flatting? This will be the same. There's not much of the differences. But still, this is very, very time consuming and taxing, so that it's just, it takes almost 40 or the 50% of their time throughout the process. And all this perspective made them feel that, oh, if you have an AI-driven tool for automating the flatting, we'd be happy to use. That was the really interesting perception about the flatting. Now let's talk about the shadowing and lighting and then special effect. they thought that this is the reason that they're just like working as a cartoon artist. They loved shadowing and lighting. They thought that this is the way they represent their skills and themselves and then their signature to the world. They really couldn't imagine if the AI can really replace that part. They had a very strong ownership. It's still just like a lot of work, sometimes depending on the way that they actually just make the production of the digital colorization. But people really expressed a high engagement. So this was very different from flatting, right? So, and well, the line drawing and then backgrounding and adding text. Line drawing is basically, they have to draw the line. There's no way other than they just draw the line. Backgrounding is largely based on a set that they have to just purchase. Adding the text is now adding the text. So this is not very closely related to AI-driven AI-driven kind of, automatization. Sorry, I cannot remember the term. So I think that after I just finished this interview, what I have found here is that, well, the colorization is actually very step-by-step. And the way that the current AI tool kind of conceived to support this colorization is combining all these steps together as one. So for example, if you see the first tool that we briefly present, everything is there. You cannot actually do the flatting, then just like add some lighting and then also add some background and then add some like speech verb and then just text. You cannot separate those things. So even if they want to just do some more control on just doing the different kind of the task in the different step, because auto colorization do everything and then they cannot make it separable. Now people cannot use this. So that's the core reason that they cannot use this AI tool. It basically doesn't care about the workflow, unfortunately. So I guess the implications, again, the implications for not considering this artist workflow in AI is that it kind of deprived the opportunity to have some control that they need. And I guess the interesting perspective is that if we deep down into what they did, and then now we really understand their perception about applying the AI automation tool is very, very different, depending on the nature of the task. And then some more laborious, repetitive, and then time consuming, and then also resource taxing type of work, such as flatting, they really want to use this AI tool, whereas more creative, let's say creative, and then their kind of signature kind of approach, such as lighting, those things, they don't need to just like have this AI. So I think that was very interesting perspective we found. So we said, okay, how about we make some AI-driven flatting tool? We suggested, and the very interesting thing happened. Some of our interviewees said, "You want to do that? I'll give you the data. Please make this tool and then give it to us." So they actually gave us more than 3,000 pairs of the images that has the line drawing and then flatting. So I guess that was, I have never just had the experience before when I just do the tool development. People generally just didn't. So I guess the reason that they really willing to just give this data, even if that was their resource, was because they really like to have this one. So that was very interesting perspective. So we were able to build a now tool without the flatting. So now our focus has been moved from the digital colorization to the flatting. We are not doing the digital colorization, only just like one sub-step of the digital colorization called flatting. Well, then is it easy if we have those data? And then we realized it's not. So, well, this is what's going on. This is the line drawing, and then this is the ground truth that we collected from our user. And then if you apply some of the GAN or PIX model, then this is the results. It's not very easy to make the high quality data. We just tried a couple of times in terms of improving the model using the 3,000 image sets. And then as you can see, you cannot do this. It's just not that easy, we found. And I guess that was our second barrier. There's obviously a problem that just disable us to move forward. It is not easy. And then I kind of thought about this, why this can happen. And this is maybe the difference of the humans and AI. We can really interpret the semantic very, very fastly. if we see these complex images, and then just like ask five years old person to draw this one, and then they can just draw this very easily. They can immediately see this is the shirt, this is the hand, this is the pants, this is the background. They can just like interpret this like with their kind of human semantic very easily. Okay, but in terms of the models to do that, now this is the line drawing, right? And then this is the research that we want to make. Well, right. So then how do AI model knows that this line is the line that just like separate the base colorization or not? There's so many complex line here. We have no problem in understanding the human semantic. This is definitely this is the hair, this is the shirt, this is the line, this is the t-shirt inside in the shirt. It's easy for us, but for AI, this is not that easy. So those small lines in the line drawing actually disable us to make the model that just really perform well. That was the problem. And I think that the really underlying the problem in here was that we have to build an AI that can really think like humans in terms of semantic. It's a very difficult task. So what should we do? It was not easy. So we just tried to just think about how we can just work on this. And then we kind of just make some similar decisions than we just did in the first time in the formative study. The task is too complex. AI cannot do this at all at once, so that we have to understand the subset, and then we just try to solve one by one. So in this approach, we decided to make a model that simplifies the line drawing. And then once the line drawing has been simplified, then now we fill the line drawing based on some filling algorithm. So we just try to split the role. So how did you do that? There's a ground truth here, and then this is a line drawing here. Right. And then using this ground truth, we just try to remove these unnecessary lines. This is the purpose of the model that we are building at this moment. So this is a step. We have the ground truth, and then we make the 1 pixel edge detection using the ground truth. You can just see very just like slight line here, you can see. And then using the line drawing, we augment this 1 pixel edge to full augmented edge. So then basically now what we want to do is to, if I give this image, line drawing, and then now the model have to make the simplified line like this. So this is kind of the framework that we call intermediate representation. We don't go directly. We just try to find a way to detour, but still better than just like directly just solving it. So that's the research. So if we give the research like this, and then using the ground truth, the flat coloring, we can just simplify the line like this. Now, once the line is simplified like this, then now it's very easy to fill the color. Something like this, something like this. Still, there's some kind of difficult problem here. The line can just sometimes kind of erase. The two cannot be perfect. Something like that. So, and if we try to simplify those lines, and then now Yotam and Chuan implemented this trap-hole filling, and then using this trap-hole filling algorithm, this is a kind of metaphor as well. You just like put the ball and then just move around, and then that will just paint the segments. This is a trap-hole. And then the results seem pretty good. Now the trap-hole filling, and then now just applying the line drawing, this trap-hole filling, then this is the results. So in that way, we were able to more or less solve the problem. So we are very happy to find this idea. It's almost done. I think that unfortunate perspective of this project is that we didn't actually run the study, although we are planning it right now. So that we just like decided to build the Adobe plugins and extension basically, so that people can actually use our tool when just they download the extension and then just click it. They can use this. Our tool is colorized. And then this is the current stage that the Chuan is just making, very impressive. So something like this. We give them some low row like the line drawing. And now model can actually just make some base colorization like this. I think that this is just way, way easier than the former approaches of just using this pen tool and just make this base colorization. Now we are just trying to merging these different segments into one. You see the small stroke here. This is the merge interaction. I'll apply this, and then now those small the segments will be merged into the one, something like this. So yeah, so far using our tool, making the one flattening research takes 6 minutes, according to Chuan. So that's a very just like impressive research, because sometimes people say it'll take more than maybe 30 minutes or 40 minutes. So we are just really excited to run the deployment study pretty soon. And this is the kind of evaluation plan. We want to run the controlled deployment study with the university students studying the digital webcomic. And then we also want to run the expert interviews with the professional web cartoon artists, so that just have some more professional ideas in terms of how the tool can actually improve their workflow or what can be done better in the future. So, well, I guess really the core ideas that I and then our team just like found in here is just really about the intermediate representation. So if we want to solve the problem directly, everything with the deep neural network, and sometimes we cannot make it because the tool, the task itself can be very complex, or it has to cope with a lot of human semantic, which I think that is very, very difficult for model to achieve. So that we have to just find a way to slice and dice the small pieces of sub steps, and then now we kind of just like understand, oh, this is the good amount of subset that the AI can achieve. Then now this is the moment that we can apply the AI. And then sometimes you don't need to even just like use this AI. And by doing so, I think that the really important perspective that we can achieve is the controllability. So when supporting the professional artists, this is all about presenting some sufficient level of controllability they want. The automation will absolutely help their life easier, make their life easier, but if we don't have a like sufficient amount of controllability, then they were not going to be able to use this. This is a deal breaker. So I guess we are just keep working on this, and then just we're expecting to run the study maybe in 2 months or so. So excited to see what's going on. Right, so that's it. Thank you very much for attending the talk and then listen to what I did. Any question, please?
If you have a question, you can unmute. We're going to stop in just a minute, but if anybody has a burning question, go ahead and unmute yourself and go ahead and ask.
So it seems like Shuhong has a question. I also want to warn all of you that I have to run to my next meeting. So I will do that after reading this. Do the artists typically draw lines digitally, or do they scan and clean pencil sketches?
Yeah, that's a good question. So if you see the past research is happening in the 2000 or 2010, Japanese artists, they were just basically made on based on the printed media. That means that they just draw the pencil and then scan it and then simplify that and they just make it digitalized. Nowadays, the web cartoonists, they rarely start from, I think, pencil. If they're working in the university, they may use the pencil, but in many cases, I found that the professional artists, they use the digital pen directly. So I guess the workflow has been just like changed a little bit, and that kind of makes the former research about this digital colorization and then line simplification a little bit less useful in the current platform.
Awesome.
Sure.
Young Ho Kim, it looks like you're thinking about asking a question. I don't know, maybe I'm wrong.
Hey, thank you for the amazing project and sharing the ideas. I have a question about a bit more of some elaboration question. Did the artists perform their drawing and kind of pipelines by themselves, or did they involve some other assistant comic artists?
Yeah, that's also a very good question. So if you are working as if you just started just working as a your career in a digital comic artist, you are the only one that you have to rely on. And then once you just get some more kind of fame and then get bigger, then now that's the moment where you can just add some more assistants. But still the interesting part is that they generally use these assistants for flatting. They don't rarely use their assistants for shadowing, lighting, or special effect. That was generally what we found. And another interesting perspective was that the main resources they had to just like financially spend was coming from the flatting in general. So there was a very just like economic considerations in terms of why they want to have these automation tools for the flatting. Yeah.
And were the comic artists from the Korean industry, or were they from?
Yeah, it's just Korean industry. Yeah.
Okay.
So the university students working in this digital comic, that's the Korean university, and then the professionals that I expect to interview is also the company in Korea. Yeah. So
Okay.
yeah, I think Korea is pretty just a good country to research this comic-based, colorization and AI support tool. I think that the neighbor webtoon, they're doing a lot of research on this, for example.
Yeah.
So
Thank you for answering the question.
yeah,
Well,
happy to do.
I do hope that people take Ray up on his offer for internships. What a great opportunity. And I do hope he gets some volunteers from the group. And I want to thank everybody for coming today. Obviously, this is a very interesting topic. This is the longest we've ever gone over, but we still have, almost 15 people hanging in here. So we're going to say goodbye for now, and we'll see you next week. And let me just tell you who we have next week. Hang on, let me just pull this up. We have Dick Horst from UserWorks, and he's going to do, here's the title of his thing, neither snow nor rain nor heat nor gloom of night nor difficulty to use websites nor COVID-19. Here's some user research that he was committed to do for the US Postal Service. So that'll be interesting. So we'll see you next week, and bye-bye, everybody. Thanks.